Welcome back to Mechanical Engineering Made Simple. Today, we are getting into the nuts and bolts, and I mean that literally, of how our world is put together. We're going to explore the unsung heroes of engineering, fasteners, and the amazing, versatile material they so often hold together, sheet metal.
Seriously, just look around you right now. Your phone, the chair you're sitting in, the building you're in. Nearly every man-made object is held together by something. Those are fasteners. They are the fundamental connectors of our world. But how on earth do engineers choose the right one? And what are they connecting? Let's dive in and start with the basics.
So where do we start? Well, let's begin with the most common fastener of all, the humble screw. Now, it might seem simple, but its design is just a brilliant piece of applied physics, and it's all centered on one elegant shape, the helix.
I love this analogy. Think about pushing a heavy box up a ramp. It's way easier than trying to lift it straight up, right? A screw thread is basically just that same ramp and inclined plane wrapped around a cylinder. So every time you turn that screw, you're essentially walking the force up that tiny ramp, converting a simple turning motion into an incredibly powerful clamping force. It's genius.
So when you get right down to it, a screw thread is a simple machine. Its whole job is to convert rotation into linear force, turning something into pushing or pulling something. And it's this single powerful principle that allows a tiny little screw to hold your glasses together and a massive bolt to hold up an entire bridge.
Okay, this diagram might look a little intimidating, but stick with me. Think of it as the DNA of a screw. That P stands for pitch, which is just the distance from one thread to the next. The D's, both capital and lowercase, are the major and minor diameters, basically the widest and narrowest points of the thread. These three measurements define absolutely everything about how that screw is going to fit and how it's going to function. For an engineer, these are the magic numbers.
All right, so we've got the geometry of a single thread down. Now let's zoom out a bit to the huge world of fasteners. Because once you know the shape you need, the next critical question is always, just how strong is it?
And this right here is where things get really, really important for any kind of design. You see, a fastener's strength isn't just about its shape. What it's made of and how big it is, those are the critical choices that determine whether it's going to hold or it's going to fail.
The numbers on this table really tell the whole story. A tiny little number 4 screw, it can handle about 360 pounds of force. A common 1/4-inch screw, that jumps to almost 2,000 pounds. But look at that big 3/4-inch bolt. It can withstand over 20,000 pounds of pulling force. To put that in perspective, that's more than the weight of 3 cars.
So what's the bottom line here? It means choosing a fastener isn't a guess, it's a calculation. An engineer has to match the screw's size and its material to the forces it's going to face. And if you get that calculation wrong, well, things can fail, sometimes catastrophically.
Okay, so we have our fasteners. We know how strong they are, but what are they actually holding together? Well, in a huge number of cases, the answer is sheet metal. It's the true canvas of modern manufacturing, forming everything from car bodies to the appliances in your kitchen. But just like screws, not all sheet steel is created equal. The two big categories are hot-rolled and cold-rolled. Think of hot-rolled as the rugged, no-nonsense workhorse. It's perfect for things like farm equipment, where looks don't really matter. Cold-rolled steel, on the other hand, gets processed more to give it a smooth, paint-ready surface and a really precise thickness. It's exactly what you need for a car door or a new refrigerator. And then you get into the specialists, the steels that get coated with other metals to gain new superpowers. Galvanized steel, for example, gets a zinc coating to fight off rust, making it perfect for anything used outdoors. Aluminized steel resists heat, which is why you'll find it in mufflers and ovens. And long-turn sheets are coated so they can be easily soldered for things like custom fuel tanks. All right, so our material is chosen. Now for the really fun part. How do you take a flat, two-dimensional sheet and transform it into a complex, three-dimensional object? That's where you get into the art of forming and bending, a core process in pretty much all manufacturing.
Before a single piece of metal ever gets bent, it has to be designed as a flat pattern. This is the 2D blueprint that, when it's folded along very specific lines, creates the final 3D part. Getting this pattern exactly right is, well, it's everything.
But wait, what about complex curves? I mean, how do you flatten a curve? This is where a super clever technique called triangulation comes in. For any curved surface that a straight edge can lie flat against, engineers can break it down into a whole series of tiny flat triangles. This lets them accurately unwrap a 3D shape into a precise 2D pattern that they can cut from a sheet. It's pretty neat.
Now this
This is that process in action. Here's how a simple C-channel gets made on a machine called a press brake. First, the outer flanges get bent up. Then, a central die pushes down, making a temporary W shape. And finally, a flattening die comes in and creates that finished channel. It's like a carefully choreographed dance between metal and machinery. So, we have our fasteners. We have our perfectly formed sheet metal parts. Now it's time to bring them all together. The final, and I'd argue most critical step, is assembly. And that requires thinking way ahead, right from the very beginning of the design.
This is a golden rule in engineering. You can design the most beautiful, elegant part imaginable. But if you can't build it efficiently, or, just as important, take it apart for repairs, then it's a failed design. This whole principle is known as design for assembly.
These two diagrams are perfect examples of what I'm talking about. On the left, see that little offset bend? That's called a joggle, and it lets two pieces of sheet metal sit perfectly flush with each other. And on the right, you can see the designer had to remember that a real person with a real wrench needs to get in there. You always have to leave room for the tools. And here's another one of those tiny details that makes a huge difference. When you bend two flanges up to form a corner, the material can bunch up and even tear. So to prevent that, designers add corner release. These little notches, they're cut into the flat pattern to give the material a place to go during the bend. And the result is a clean, strong corner instead of a ripped, weak one.
So as you can see, it's all a system of interconnected details. The pitch of a screw, the grade of the steel, the sequence of the bends, that tiny relief notch in the corner. Every single choice has to work together to create the final product. Nothing is an accident.
So I'll leave you with this. The next time you look at your car, or your microwave, or even just a simple metal bracket, think about its journey. Think about how it started as a flat sheet of metal and a box of screws. What hidden details, what clever design choices can you spot now? Thanks for watching.